State feedback in state space systems is convenient and quite elegant. However, the unfortunate truth is that the reason why we have this output equation is because y is really what we have access to based on the sensors of our system. And so that's what C actually encodes. It encodes which of these states X we can actually see. And so what we're going to look at now is what kind of feedback we can accomplish if we don't actually know the state X, but that we can only observe the output Y. And this is going to be true even for a case where we have multiple outputs, but in this course we consider only cases that have single output. And notice if we don't know X, then we also don't know the initial condition of X. And so what we're going to do is we're going to build a second system that mimics the original system and is created such that it produces an estimate, which we're going to use the notation x hat. And this estimate, what we want to show is that the estimate converges to the actual state x as time goes on. And hopefully it does this relatively quickly. Our approach is to design a dynamical system that is in fact a dynamical system where the variable is the estimate x dot. And so this is the derivative of x dot, and that's equal to ax hat plus bu. So that mimics exactly the differential equation of x. Now what we're going to do is we're going to add essentially a adjustment term, and this adjustment term is dependent on the error, essentially the error between what we see the system doing, that's our observations y, and then what we predict based on our predicted state. So if we know what the C matrix is, then we can express based on our estimate how close we're doing, how good a job we're doing in terms of how well our estimate predicts what we're observing y. And so we're going to adjust how much we pay attention to those that error in observation by using this matrix L. And again, P for us is oftentimes is 1 for pretty much all the systems that we are looking at, but this does generalize very nicely. And so this gives us, this L is our degree of freedom in designing this error. And designing this estimate that produces an error. And modeling that error is going to be one of the ways that we keep tabs on how well we're doing in terms of estimating the state. And so the error that we would use to describe how well we're doing estimating the state is just given by the state minus our estimate. Again, we don't know the state in real time, but this analysis is being done offline. And so if the A matrices are the same, then that allows us a way of simplifying the two systems. So we can look at the evolution of the error, E dot, and that's just the derivative of both of the terms, x dot and x hat dot. So we can plug in what those two terms are. So this is x dot, and this term in brackets is x hat dot. And so the fact that we use the same A matrix and the fact that we know the common input U and all the matrices are the same allows for some simplifications. So these two BU terms cancel, and we can combine the two terms with A. And so that gives us A multiplied by the estimation error again. So that quantity x minus x hat appears again. And then we have a term here where if we substitute y as being c times x, then we can factor out a c, and we just get L multiplying c multiplying again the estimation error E. And so this means that we have A times E minus LC times E, and if we combine that together, then we get this equation, E dot is equal to A minus LC times E. And this again should look very similar to x dot equals ax, in the sense that the dynamics and the behavior of the system is determined exclusively by A. So that means that the dynamics and behavior of this system, the estimation error, is given entirely by the matrix A minus L times C. And so if we want E to go to 0, if we want the error to stabilize, which means that the estimate goes to the state value x, that we want the eigenvalues of A minus LC to be such that the real parts are less than 0. So just like what we talked about in the state estimation part, now we have another criterion here that says that we want our estimation error to also go to 0, and so that gives us conditions on this matrix A minus LC. The cool thing that we can do now is we can, instead of using our state feedback, which is what we used before, we can now use our estimate instead. If our estimate is doing a good job of looking very similar to our state X, then that means that we can use the estimate instead of the state X. And so now it means that our control U is just given by K times our estimate X hat. And so we can substitute that into, when we see U of t in our X equation, we can substitute that in, and now we have K times X hat. And X hat, again, remember X hat is simply just the difference between X and the estimation error. And the value in doing this estimation error, substituting this for X hat, is the fact that we have an equation that represents the estimation error dynamics. And so this means that we can pull this term of X to combine it with this term of X, and we get our A plus BK, which is the same matrix that we had before for state feedback. But now we have this term, and this term is dependent on the estimation error. And the estimation error evolves according to this set of equations. And so what's really cool about this, and this is one of the culminating points of modern control theory, is the fact that when you combine these two equations together, don't be confused, X is a vector and E is also a vector, but we can still combine them into an even larger system where this is a block matrix. So this is a block that represents a matrix. This is another block that represents a matrix, and same here. And this triangular structure of this matrix is the culminating point, and what it tells us is that the eigenvalues of this overall matrix are essentially the eigenvalues of this matrix combined with the eigenvalues of this matrix. And so if we want this overall system, including X and E, to be stable, then that means that we need to design K and L such that the eigenvalues A plus BK are stable, and the eigenvalues A minus LC are stable. And what's cool is that there isn't any overlap between these. So there's no L term in this statement, and there's no K term in this statement, which means that we can design these independently. Again, designing these will be a subject of a future class, but it's revealing to go ahead and show this so that we can understand from an analytical point of view what are the requirements for a state space system under state feedback and under estimate feedback for the state, and in this case also the estimation error, to be stabilized. And so in this case what ends up happening is we have our plant, which represents our original system. C denotes which elements of the state vector X that we're actually observing. Those observations Y are being passed back to an estimator. That estimator produces X hat. That X hat is used with the gain K in order to multiply the X hat to get our input U. That input is sent back to the system, and it's also used when we compute our estimate using the estimator. So we'll build on these ideas in class and start to look at the topics of tracking.